section, we went through a bunch of limits, right? We did a bunch of limits. We did limits that the limit didn't exist. We had sort of limits that you find two paths, that the paths were straight and the limit were different. Then we did at least one that all the straight paths would give you same limit. So either limits agree or they don't agree. Paths are just for us to prove that the limit doesn't exist. So we have, if we cannot find paths that the limit doesn't agree on those, we have to find another method. And here's one example that is difficult to always find a path. Sometimes you have to have a little bit of experience in it to find a path, the two paths that give you different limits. So that's another one. And then I'm going to go back to that. And then we did a bunch of limits that existed. We used polar coordinates. With the first one, we used L'Hopital rule. With the second one, we used, what did we use for the second one? Squeeze lemma. I want to tell you something in advance. Plug in your R and theta. Let me write this down. These are the review. We can use two paths that don't agree. One of the methods that we so far learned is plug in polar coordinates. Polar coordinates tells us that the distance is getting smaller and smaller. Then use some other method. So far we did L'Hopital and squeeze theorem. So one thing I want to say about the squeeze theorem. Squeeze theorem is equivalent to saying that you have two functions. Let's call this f of r. Let me rewrite it. F of r, g of r and theta, right? And f of r is going to 0. The limit of f of r is 0. And g of r and theta is bounded. Do you guys know what bounded mean? Anybody knows what bounded mean? Bounded, do your hands like this. Bounded is exactly this. There is a number that the function cannot be, the output of function cannot be bigger than, and a lower bound is the number that the output of function cannot be smaller than. So here, bounded means that g of r and theta is between big M and L, for example. Two numbers. Number and number. And so when one function is bounded, the other function is going to 0, this is equivalent to a squeeze lemma. After you plug in your r and theta, you want to figure out if you can pull out r, and what is left over is bounded, and r multiplies and makes it 0. Now, there is an example in here that this is not true. So let's see, if I plug in, let's try to plug this in. And this is how I know that, let me put this here. Get rid of that. Here, if I try polar, what do I get? Limit r squared. Cosine squared theta, everybody agrees on that? Sine squared theta. What is the denominator? R squared. R goes to 0, theta, I don't know. And then I feel like I should be able to, if I plug in r and theta, I should be able to use squeeze lemma. But when I do that and I factor r squared on top, this trigonometric function should look familiar to you. What is that? Cosine 2 theta. So I get limit of r goes to 0, theta goes to whatever, cosine of 2 theta. Looking at this, the part, do you see I said two functions, product of two functions? One of them was supposed to go to 0. That didn't happen to me, right? So the part that you're doing squeeze lemma is often like that. You have a part that goes to 0 and a part that is bounded. But this part is bounded. So someone says, what if I do this? Can I still find two paths? You could find two paths. I can say theta equal to 0, limit is going to be what? 1. What else can I put in there? Theta equal to pi half. What is the limit? Cosine of 2 pi half, cosine of pi, -1. So that technically gives me a path too. So it requires you doing a few problems until it becomes a little bit more clear. But here it is. So this one didn't have a limit. When I tried r and theta, what happened? When I tried r and theta, I found a bounded function only, which is not giving me a limit because there's nothing going to 0 multiplying it. Can everybody see the difference between this and the problem before that? Let me bring it up. See the difference between this one and that one. That one, I still had an r in here and everything else was bounded. Here, this is bounded, but there's no r multiplying it, or r squared multiplying it, or anything like that. Did that clear stuff out? Can I go back to iClicker? Are we ready? Okay. I talked too much? Is that it? Okay, this is B. Go on, guys. Let me start it. Now go on, please. I'll go this way, you go that way, we switch. Which one? That one? Oh, yeah. Oh my, sorry about that. When the person before me doesn't leave it, it's just harder to set things up. And then I forget. So what should you do? First, plug in x equal to 0, see what the limit is. Plug in y equal to 0, see what the limit is. Then plug in y equal to x, and then y equal to -x. Are you getting different limits from any of the pairs? This is going slow. Questions? Who has found an answer? Did you talk to your neighbor about it? Talk to your neighbor about it. Did you guys find an answer? No? Have you plugged it in? So if I plug in x equal to 0, what is the limit? 0. If I plug in y equal to 0, what's the limit? So somebody said if I plug in x equal to 0, I get limit 0. Y equal to 0, I get limit 0. Is that useful? Is A useful? Not at all. Both of the limits are the same. That's not what I use the paths for. So what about the second one? What about B? Plug in y equal to x. What do you get? If I plug in y equal to x, what's the limit? Is everybody getting 1/2? So how about negative x? Y equal to negative x. So is B useful? Okay. So how about, let's do one more maybe, C. How about C? Limit So what is the limit when I'm plugging in y equal to x squared? What about negative x squared, do you think? So is C useful? No. Same thing happens actually in D. Did everybody get the answer? Okay, can I stop this? Yes, somebody said no? Who said no? You got the answer? Okay, 4, 3, 2, 1, 0. Wait, we decided that A is not useful because A, for both of them, for y equal to 0 and x equal to 0, I get limit of 0 over something as x goes to 0 is 0. So both of them are the same. B, as y equal to x, I get x squared over x squared plus x squared. X goes to 0, 1/2. Y equal to negative x. Not equal limit D and E. Useful. So check mark. So that was the answer. Now, one more. Are you guys ready for one more? Who's ready for one more eye clicker? Okay, thank you. Oh, should we switch? Talk to each other, by the way.
We plug in for 0.
So, my question is, you have two methods to know whether or not this exists. Right? Remember the first problem I did today, still up there. Over here. What was the issue here? What was the issue on the right problem, right? Example 8 over here, where the limit didn't exist. What was the issue? R completely simplified from top and bottom. I didn't have a function of R multiplying, making it 0. Is that the case for that if I plug in R and theta? Does R simplify entirely or R stays? Can I use squeeze theorem if R stays and the other function is bounded? No. That's what it is. Did that make sense? What I said, did it make sense? I know Ian. I know Chloe. I know his name. I just can't remember.
It's Sylvan, not Chloe.
Your roommate. Who's Chloe? Chloe looks exactly like you. Short, pixie hair.
It's Eli.
Eli, not Ian.
That's honestly, I get called Ian a lot. So.
Ian a lot. Oh, sorry. No, I mean, how's it going here? Good? Okay.
Approaching 0, 0.
So if I approach 0, 0 from any direction you give me, I start doubting myself because they're all giving me 0, right? So, but I can't prove that the limit exists. So I have to use the method with R and theta in this case. Oh, by the way, there is another method that they discuss in your lab. We don't discuss in lecture. Beside R and theta, there are the other methods in there. They discuss one in the lab. We can't discuss all of them. I mean, there are many other methods on top of that. We just discussed 2, one in lecture, one in lab. So if I plug in R and theta, what happens? When I plug in R and theta, what does it simplify to? R times do it faster, do it faster. Faster. Plug in R and theta. What does it simplify to? Somebody please read it to me. How many factors of R on top? 5 with R4? R. What about this? Is this bounded? What are the bounds? 1 and -1, right? So bounded times something that goes to 0 according to squeeze theorem. What is that? Okay. 4. 3. Michael. He said he is getting scared. Can you check her work for a quick minute? She's sitting in front.
Okay,
is it
yeah,
okay?
I know you're talking about. Yeah, she's like the back front.
Is she doing okay? I don't want to.
Yeah,
Okay. So 4, 3, 2, 1, 0. B is the answer. It exists and is equal to 0, according to that rule. Do you want to do one more quickly or not? Do one more quickly. This time, be quicker. Last time it was too quick, too lengthy.
Is it 4?
Can I put in R and theta? Can I put in R and theta? If I put in R and theta, what happens?
It's bad.
What's the factor R in the numerator? What's the factor of R in the denominator? 4. 4 R to power 4, right? The 4 factors of R, which R to power 4. Now, they simplify, and what is left does that have a limit or is just a bounded useless function? Bounded useless? Right. So can you give me two paths that give me different limits now? Now that we tried that way, wasn't working, try to find paths. What paths are you suggesting? Y is equal to 0, it gives me what? 0. What about y equal to x? I have to compute. 2 in the bottom, 4 in the top, yes. Okay. Can I count down? No.
I think the hint here is
What up?
I simplified that correctly.
Is this one? So you had r to the 4 on the bottom, right? And then, oh, here you forgot. It's r cosine theta to power 3. So you get r3 times r. This is 4 r to 3 cosine to 3. You good? Everybody's good? Anna, you good?
Would it be if it's just 0 since it's multiplied on the top of it?
No, R4 and R4 simplify, right?
Yeah.
So what is left is cosine to power 3 theta, sine of theta. And that doesn't have a limit. Yes? How do I simplify the denominator? You don't, oh yeah, this denominator doesn't simplify. Look at this, it's not even bounded function, you're right. It's r to the 4 times cosine to power 4th of theta plus sine to power 4th of theta. It may not even be bounded. It's useless and maybe unbounded. So both of them.
Doesn't this go 0 to the 4th?
No, you have to power r3 times r4.
Oh, sorry.
Okay.
I think
Yes.
do you always have to first try and plug in R?
See, a lot of times it gives you intuition. When you plug in r and theta first, it gives you intuition. Yes, I say plug in r and theta first in your head if you don't know the limit exists or not. It gives you some intuition.
I have a question. So if that doesn't work, then you obviously go to the different paths.
Different paths.
So would you always second one, would you always try and y
Try to
equals
find the
0,
paths,
and
yeah.
then x, y equals x? Is there like an order?
Sometimes you can see quickly that those don't work, like the one that we did. But it comes with practice.
So I know that you said x4 plus
Oh, you use that? That's okay too.
but that doesn't simplify to r,
No, it
or
does.
does it?
All of them
Is
simplify.
r to the 4th the same as x to the 4th plus y?
No. This simplifies to r to the 4th. Let me write it down.
Okay.
Okay, so I'm going to write this down. I'm spending a little bit too much time on this. Hold on. When I'm trying to simplify this one, limits of 4x cubed y over x4 plus y to the 4th, x and y goes to 0, 0. When I plug in r and theta, what do I get on top? I get r cubed cosine cubed theta, r sine theta. What do I get in the bottom? R 4th cosine to the 4th theta plus r 4th sine 4th theta. Agreed? Now factor the r's out. 4r to the 4th, r to the 4th. What is left over is this. Agreed? These two simplify. I still have the limit. If you don't put the limit in, I'm going to complain. Now then, the r is gone. I don't even know if this has a bound or not. But as I'm looking at this is changing. For different theta, I get different values. right? Before even I look for paths, I can see this is changing. Everybody agrees on that? So that cannot have a limit because it's simplified to this. This does not exist. But on the exam or on the quiz, I'm going to ask you to give me exact two paths because we want to show it mathematically. So someone said, how about y equal to 0, one path, and then limits would be going to 0, and then they said find y equal to x, which limit is going to be 2. And then that would give me the DNA. Did everybody get that? I did the problem. Almost. Just the last piece I didn't do. Everybody okay? Nick, you're approving? Nick approved of this message. 4, 3, 2, 1, 0. Okay. Let's move on to the next section. Again, there are methods that we didn't cover today. It's going to be covered in a lab. And on top of that, with limits is practice, practice, practice. What did I do? Do you see full size? There we go. Okay. Can I get your attention to the new section? Is everybody going to the new section? Yes. Let's go to the new section. We are going to talk about partial derivatives. Partial derivatives, some of you have seen it either in your engineering courses or in physics courses or chemistry. How I'm going to say, I'm going to reteach that again, but also something that you definitely haven't seen is the geometric meaning of partial derivative. A lot of times, geometric meaning is very, very important when you get to Calc 3. Having that picture in your head is sometimes more important than being able to do all the computation. That's something that I want to tell you. So I start with talking about derivatives. Do you guys remember what was the derivative in Calc 1? Let's see, what was the f prime of I? How did I define f prime of A? Do you guys remember that? What was the other one? How did I define the function f prime of x? Right? So this was how we defined the Calc 1 way. But Calc 1 was nice because I was saying with a small change in what variable? X. With a small change in x, I want to figure out what's the average rate, average change, basically. It was always small change in x. X was significant of x was an input. Now, how many variables do you have now? 2 or more, right? So now the problem is with a small change in each of those variables, what is the average change in the output? Andrew, it's going to be okay. It's going to be okay. It's going to be okay. So now, another thing that we learned in Calc 1, the derivative at the point represented our slope of the tangent line. Now let me show you some stuff. Oh, I forgot to bring that thing up. the problem becomes, first of all, what is a tangent line, right? I forgot my manipulation, the device. That's okay. So I have this surface. My hand is a surface, right? And let's say this is the x direction, this is the y direction. My hand sits on top of it. Everybody okay with that? Now I want to figure out at a point on my hand right there. It will hurt a little bit. No, it's not working. I forgot my, I do have a model. I forgot to bring it. It was on top of my bag. I forgot it. So here's a point, right? First thing that you want to do, you want to find a cross section in the x direction. That's a curved cross section on x direction. Another cross section on the y direction. Two curves on my hand, right? They're not straight. They're curves. And then you want to find a tangent line to that curve or a tangent line to this curve. Can everybody see what I'm doing? Is it obvious? So here's my hand, one point on the surface of the graph. Then from that surface of the graph, you do two chops. Chops in the x direction, chop in the y direction. Then each one of those chops, so the cross sections, is a curve in two dimensions. Find the tangent line for that. And that slope of those tangent lines are your partial derivatives. Fair game? So pictorially, that's the cross section. What is that cross section? In y equal to b. Y equal to b fixes y. Cross section in y equal to constant fixes y. So the curve that you get only depends on x. The curve changes with x, not with y anymore. Cross section y equal to constant gives you that curve. And then I can take the derivative of x basically with respect to x. Do you guys need to talk about this for 10 seconds? Do it. 10 seconds talking about it. Are you okay? You okay?